let's quickly recap what we know about quadratic functions. First, there are two primary forms of the equation for a quadratic function. There is the standard form, ax squared plus bx plus c. And then we also now have the vertex form, which is a times the quantity x minus h squared plus k. And we have the ability to convert between the two by completing the square. Each of these gives us different types of information. First and foremost, a cannot equal 0, because if a equals 0, we don't have a quadratic. The vertex is given in the vertex form. It's at hk. The value of a is the same for both. What it does is it tells you the relative width of your parabola and whether or not your parabola has a maximum value or a minimum value. And then the standard form gives us the location of the vertex in a different way by using the line of symmetry, which is negative b over 2a, and then the function value of negative b over 2a gives us the y value. So what I want to be able to do is I want to be able to take any graph of a quadratic function or a table of quadratic data and write the equation for that function. Now, there is a subtle difference between writing quadratic equations and writing quadratic functions. And we're going to look at two theorems that will help us write the equation for a function. Now, I'm going to tell you this right now. You know how when you were writing equations for lines, you needed 2 points? Because by definition, any 2 points define a distinct line. Well, something similar holds for quadratic functions and parabolas in general. But instead of 2 points, I need 3. So if you want to write the specific equation for a quadratic function, whether it's a table or a graph of the function, you're going to need 3 points, all right? So that's sort of a key thing here, is if I want to write a specific equation for a function, I need 3 points, all right? Now the two theorems that are going to help us write equations for quadratic functions actually only use 2 points, so we're going to have to do a little bit of extra work. So as I said, there are going to be a couple of theorems that are going to help us write quadratic equations for functions, and this is the first one. It says let R1 and R2 be roots of a quadratic equation. Then the equation will be x squared minus the sum of the roots plus the product of the roots equals 0. Or this same equation multiplied by some constant a. Now this is not the rule to write a quadratic equation for a function, a particular function, but just a quadratic equation in general. And the reason why is this theorem only uses 2 points, which are the 2 roots. And I need a third point to pinpoint the exact function. So let's look at this example on the graphing calculator. I've typed in 5 quadratic equations that all have the exact same roots at 3 and negative 3. And what I did was I changed the a value. And so if I graph these, what I'm going to see is that I have a bunch of parabolas that have the exact same roots at 3 and negative 3. And so this theorem doesn't give me a specific quadratic function. What it does is it generates a way to have a bunch of different equations that have those roots. So I need that third point to kind of pinpoint specifically which parabola I have. But I can still use this. Now, before I actually use this, I want to make sure you understand where this comes from. And so if I think about what I did on the graphing calculator, I know that I can take the 2 roots R1 and R2, and I can write those as factored form, right? So it's x minus root 1 times x minus root 2 equals 0 is going to give me a quadratic equation. And then I just have to multiply that out, and I get x squared minus r2x minus r1x plus r1 r2 equals 0. And then I just have to factor out the x and the negative, and I get x squared minus, and I'm going to just reorder this as root 1 plus root 2, x plus root 1 root 2 equals 0. And so that's where the minus the sum of the roots plus the product of the roots comes from. So now let's look at an example really quick. So let's say I want to write the equation for a quadratic with roots 3 plus I over 2 and 3 minus I over 2, right? And so I can just use this theorem that says that I can just take x squared minus the sum of the roots. So then I just have to add these two roots. So I get 6 over 2 or 3. And then multiply these two numbers together. And if I just multiply 3 plus I over 2 times 3 minus I over 2, I'm going to get 5 halves, and I have my equation. So this is the equation of a parabola with the roots at 3 plus I over 2 and 3 minus I over 2. And I can generate a whole bunch more quadratic equations with these exact same roots by just multiplying it by some constant. So for example, if I wanted to get rid of the fractions, or if I gave you the instruction, write the equation for the quadratic with integral roots, meaning roots that are integers, you can just multiply the entire equation by 2 and get 2x squared minus 6x plus 5 equals 0. So as a separate theorem, and something that's more like a corollary to the theorem you just saw, if I'm given R1 and R2 are roots of a quadratic equation, and ax squared plus bx plus c equals 0, then the sum of the roots is equal to negative b over a, and the product of the roots is equal to c over a. And you can really easily show this is true by just taking the ax squared plus bx plus c and setting it equal to the a times the x squared minus r1 plus r2 plus r1 r2, and then just realize that this has to equal b, and then go ahead and do the division and you can get this. Now it doesn't really help us write equations for quadratics, but it does give us a good way to check our solutions when we're solving, because we know that the sum of the roots is exactly the same as negative b over a, and the product of the roots is c over a. So if I can find the two roots, add them, and multiply them, I can verify that they are indeed equal to those two quantities. So we just saw the theorems that help you write equations for quadratics given the roots, but those equations actually generate an entire family of equations that have those roots. So if I want to specifically write an equation for a given parabola or a given quadratic function, I need a third point. And the easiest scenario is if I give you the roots and the other point. Because then you can use the two theorems we just saw and then just solve for a. What's a little bit trickier is if I just give you 3 random points where none of them are roots. So let's look at how to deal with the first type of situation. So for example, let's say I tell you that a graph has x-intercepts at 1 and 3 and a maximum value of 10. This is enough information to write the equation of a specific parabola. And so if I want to, I can just sort of do a quick sketch to see what kind of information I have. I have an x-intercept here at 1, I have another x-intercept here at 3, and I have a maximum value up here at 10. So by knowing the features of a parabola, primarily that parabolas are symmetric, then I can work backwards to figure out the x value for that maximum, which in this case is 2. So this vertex is located at 210. And then I also have the point 1, 0, and I have the point 3, 0. So that's enough information for me to write my quadratic function for a parabola that has these set of criteria. And here's how I do it. Well, I need to find the sum of the roots and then the product of the roots. So the sum of the roots is 4, and the product of the roots is 3. Therefore, I know that my quadratic function has a base equation that's x squared minus 4x plus 3, and it's multiplied by some a value, like so. And now I just have to find the a value, and that's where I use this third piece of information. And what I'm going to do is I'm going to substitute in the 2 and the 10 into this to solve for a. Now I know f of x, the function value, is 10 when x is 2. So it gives me this equation to solve. Now, using the order of operations, I can get 10 equals a times negative 1, and therefore a equals negative 10. So I have a specific function equation now. F of x equals negative 10x squared plus 40x minus 30. So now let's talk really briefly about how to write the equation for a parabola given just 3 random points on the parabola. Or if you get a table, how do you write the equation for the table when the points given are not roots and you don't know if you have the vertex or not. So I have 3 random points here. And actually, what I want you to do is I want you to figure out a way to write the equations for this parabola. Now, I'm going to give you a hint. You are trying to find A, B, and C for that equation, and that's the only hint I'm going to give you.